two possibilities exist. Either we are alone in the universe, or we are not. And as science fiction author Arthur C. Clarke famously pointed out, both are equally terrifying. For decades, our search for an answer has been driven by a serious blind spot. We suffer from a terrestrial bias. When we look up into the night sky, we instinctively search for perfect mirrors of our own planet, worlds with familiar atmospheres, comfortable temperatures, and exact carbon copies of our own biochemistry. But that narrow view ignores the evidence right under our feet. Life on Earth thrives in the pitch-black, boiling waters of deep ocean volcanic vents and clings to the freezing rock of the Himalayas. As long as you have basic energy and water, biology finds a foothold. To understand the true evolutionary playing field, we have to look at the scale comparison chart. This shows our single Earth, measured against the estimated number of habitable planets out there. That number is roughly 10 billion trillion. With a volume of worlds that massive, the raw ingredients for biology are stewing in every conceivable environment. Nature has to obey the strict physical laws of chemistry, but across trillions of different planetary environments, the ways those chemicals can combine and adapt are practically infinite. The search for alien life represents a mapping of the absolute physical limits of evolution. The first rung of that evolutionary ladder starts with convergent evolution, the tendency for unrelated species to develop similar physical traits to survive similar pressures. On rocky exoplanets, alien life might still develop familiar tools, like eyes to see or leaves to gather sunlight, but those tools will be uniquely warped by local physics. Take a planet orbiting a red dwarf star. These stars are incredibly dim, putting out only a fraction of the visible light our sun does. To survive, vegetation there would evolve pigments designed to absorb every single available wavelength, leaving the flora completely pitch black. Planetary gravity also acts as a relentless evolutionary sculpture. On massive, rocky super-Earths, gravity pulls down on organisms with crushing force. Simply moving across land requires serious structural support. Complex animals would need squat, ultra-dense bone structures and robust circulatory systems just to pump blood against the heavy downward pull. Reverse that gravitational pull and evolution stretches out. On small, low-gravity planets, the energy cost to move nutrients upwards drops significantly. Plant life could easily rocket to towering heights, while animals could develop elongated, spindly bodies that would snap under Earth's pressure. A towering, spindly creature living in a black forest might look like a monster to us. But if they share our carbon-based biochemistry, shaped by those familiar environmental pressures, they are chemically related to us. They are our cosmic cousins. But the universe gets much weirder outside the comfortable warmth of a star's Goldilocks zone. When an environment is too frozen for liquid water and too hostile for carbon, matter still tries to organize itself. Deep in the outer solar system, moons like Titan are covered in vast lakes of liquid methane at hundreds of degrees below zero. In these frigid conditions, a completely different biochemistry becomes possible. Life could rely on the element silicon instead of carbon, drinking from those methane oceans and drawing energy from the rock itself. We can look even further away from traditional biology. Plasma, a volatile, ionized gas, makes up most of the observable universe. When simple cosmic dust interacts with this plasma, the inorganic particles can spontaneously lock together. They form twisting, self-replicating helical structures that behave exactly like DNA, entirely without carbon or water.
Pushed to the absolute extreme, and we find neutron stars. These are the crushed, ultra-dense cores of dead suns. The gravity and heat are so intense that atoms are stripped bare. Yet some physicists theorize that subatomic particles inside that swirling, boiling sea could link together into supernuclei, living, evolving, and dying in fractions of a microsecond. Habitability is entirely relative. Life is a relentless property of matter, constantly organizing itself under any condition the cosmos throws at it. If life is a universal property of matter, then eventually that organization reaches a threshold of self-awareness. When an intelligent species begins to process information faster than its environment can kill it, the ladder reaches a new rung. the species begins engineering the environment to suit itself. Scientists categorize these highly advanced post-biological civilizations using the Kardashev scale. This framework ignores what an alien looks like and instead measures them by a more reliable metric: how much energy they consume. A Type 1 civilization is learning to harness the total energy of its home planet. To find them, astronomers search for technosignatures, unnatural chemical fingerprints like chlorofluorocarbons. Spotting these pollutants lingering in an alien atmosphere proves someone down there is running an industrial society. A Type 2 civilization makes a staggering leap. They have mastered their entire host star. To capture all that solar output, they might construct a Dyson swarm, millions of orbiting megastructures that encase the sun. We would be able to spot this by looking for the distinct, unnatural transit dimming caused by all that metal blocking the starlight. A Type 3 civilization commands the energy of an entire galaxy. They engage in projects that dwarf entire planets, such as starlifting, physically harvesting heavy materials directly out of a star's core to extend its lifespan, or manually rearranging solar systems into artificial configurations to maximize habitable real estate. By stripping stars for parts and re-engineering planetary orbits, these beings physically shape the architecture of the cosmos itself. This brings us to a crushing paradox. If the universe has the physical capacity for everything from methane-drinking microbes to galaxy-engineering machines, where are they? We have pointed our instruments at the stars for decades, and we have been met with absolute silence. This silence fuels a deep existential dread. It suggests that complex life might be impossibly rare, or that industrial societies inevitably destroy themselves. We look up and wonder if we are searching a cosmic graveyard. To understand this chart, we have to realize that our perception of time is heavily skewed. This visualization plots the lifespan of the universe. Our cosmos is close to 14 billion years old. That sounds ancient to us, but red dwarf stars will burn steadily for over 100 trillion years. Measured against its total lifespan, the universe is barely a toddler. The cosmic chemistry set has only just cooled down enough to get started. When you calculate the math across those deep time horizons, it reveals that the vast majority of habitable planets in this universe have not even been born yet. Earth's emergence coincided with the first generation of stable planets, making us a first-row audience to a universe that is just beginning to unfold. We are the first pioneers in a very long story. Solitude in a young universe provides a unique window of opportunity. With nearly 100 trillion years of starlight ahead, we are the first generation with the time and resources to attempt a leap across the stars. We have the first move in an unfinished story.